Hello everyone. In today's lecture, we're going to introduce something that's pretty exciting. We've talked a lot about statistical modeling. In this class, we've done a lot with different sorts of data. But in this lecture, we're going to introduce the idea of how we can generate and prepare actual earthquake time histories to use in a response analysis. So a lot of different engineers in industry use these skills, whether they're structural engineers or geotechnical engineers. So hopefully you'll find the information that you'll get from this lecture useful. One thing that I want to say right at the start of this lecture, please, please, please do not think that the things that you're going to learn in this lecture and in coming lectures where we do some demonstrations with time history development, please do not think that you're going to be an expert right off the bat. The point is that my goal is to train you and teach you enough to make you dangerous, but not enough to make you an expert. Really, what you need is to go and work under the tutelage and guidance of an experienced and reputable earthquake engineering mentor out in industry. And to learn this stuff really well takes years of practice and experience and building your own reputation. And so the things that you're going to learn in this lecture and in the lectures to come related to time history development will assist you in gaining some reputation within your future company and impressing this potential mentor who will train you and teach you more and more. But please do not think that you're going to be an expert immediately when you walk out of this class. The things that we're going to be talking about here are pretty sophisticated and advanced, and so they take a lot of practice and a lot of criticism to fine-tune your skills and to get better. So I want to just pause and point out, look how far you've come in this semester. We've done a lot of stuff. You've learned a lot about seismology, about the earth, about earthquakes and different wave types. You've learned about ground motion parameters and how we can quantify an earthquake. You've learned about attenuation relationships and how we can use those models to predict ground motion parameters for some future earthquake at a site, and doing that in a deterministic or a probabilistic manner. You've learned about different types of spectra, Fourier spectra, response spectra, and all of these things are really advanced topics, and so you should be proud of yourself and see just how far you've come. Today's topic is going to be new to a lot of you, but it's going to be exciting because we're going to start to make use of all of those time histories that have been recorded since the 1940s. Time history analysis is when we build some sort of response model, whether it's structural or geotechnical, and we use actual time histories in the model to see what's going to happen. Usually these models are a time-based analysis, or they're in the time domain. So the model steps through each time increment and computes the response of the different nodes of the structure or the soil. So for instance, this picture that you see on this slide here is just an example of a dynamic SAT 2000 model of some steel structure that when you look at down on the base of each of these columns, you see little springs. That's where the ground motion is going to come into the model, and it's going to shake the entire structure. So when we do a time history analysis, really the goal is to use time histories that are representative of the potential design earthquake that we're expecting at our site. But that's a problem, right? I mean, it's hard enough to try to predict ground motion parameters from some future earthquake that hasn't happened yet. But now try predicting an entire earthquake time history for some earthquake that hasn't happened yet. That's a really tall order. And so one of the things that we commonly do today to try to guide our development of time histories is we try to use the design response spectrum as a target for our various time histories. And, you could ask this question, well, why do we do that? Take a look here at this picture that we have. So in this line, you see that we have a design spectrum where the arrow's pointing. Maybe this was developed from the IBC code. So that's really what the code is saying is the standard we should be shooting for designing whatever structure we're designing. And then you see all below it, you see numerous response spectra from real earthquakes, a whole bunch of them. And if you compare the response spectra from the real earthquakes with our design response spectrum, you can see that for the most part, all of the real earthquake spectra fall below, and in most cases, well below, our design response spectrum. So what would the problem be in this scenario? Well, the problem would be that the time histories we'd be introducing to our model would be inadequate compared to the design spectrum or to the level of seismic loading that the code says our structure should be designed for. Ideally, we would want time histories that could get very close, if not as close as possible, to matching that target certainly across the periods of interest, if not across the entire spectrum. So to do this, there's really two main methods that we're going to introduce that we use today to develop our time histories for these types of analyses. The first method that I will talk about briefly is called time history scaling. And this is a good method where we're going to use real, actual, raw time histories, and we're just going to modify them or tweak them slightly to get them to where we want them to be. I'll explain more when we get there. The second method is called spectral matching. Now, this is a more rigorous, more analytical approach where we're going to use a computer algorithm to modify real-time histories to get them to closely match target response spectrum. Let's first talk about time history scaling. So when I say scaling, really what I'm talking about is adjusting the time history's scaling factor. So that would be scaling its spectral accelerations across the board, and or adjusting the time history's time step to try to shrink or fudge the period of our response spectrum to try to meet some sort of target. So here's a great example. Let's say that for a particular structure that we're designing, it has a natural period or a period of interest of 2 seconds. So I can go and select, say, 20 time histories. And each of these little lines that you see here is a time history from one of the 20 earthquakes. And this big black line that I'm now outlining in red, which I'm going to have to erase because now that's confusing because you have multiple red lines on there. That is the target spectrum that we're shooting for. That's, say, from building code or something like that, okay? So now the goal is, how do we pick time histories that are going to get us really close to our target codified spectral acceleration at our period of interest? So imagine if for every one of these little gray lines here, or the individual response spectra, that we multiply or divide that the entire response spectrum by the factor such that at the period of 2 seconds, I have this response spectrum that corresponds with my target. In other words, we're going to fudge all of our response spectra so that they run through that exact same point at our period of interest. Now, the reason we do that is so that we can hit our structure in our model with the right spectral acceleration at the critical period. But see, now we've got maybe a challenge, or it depends on who you're talking to. Some people call it a challenge, other people call it a good thing. If you look at any other period along this in our spectrum, you can see that, man, we have a really broad range of spectral accelerations that we're dealing with, such that anywhere in this range here, we could expect to get a spectral acceleration at those different periods. And all of that different variability, some would argue, is a good thing, because what it's doing is it's introducing natural variation from earthquakes to our model. Other people would say, well, how in the world could we possibly interpret anything with all that variation in there? We would have no idea to know, say something performs inadequately. Is it because it got hit by an unrealistic ground motion? Or is it because something's wrong with the structure? How are we going to know? So, both arguments have really good points. I think the idea is that if we take, say, the median or the averaged response spectrum from all these different time histories we have in here, it's hard to see because now I'm coloring over a red line with a red pen. Maybe I'll change the color. Let's change it to blue. Okay, so now I'm coloring blue. If I take the average of all of those, it's going to draw something that looks, something like this. And the goal is that that average response spectrum should be pretty close to our target response spectrum in the first place. So we're not so worried about individual response spectra, but more the average of all of the series that we're looking at should be close to our target. So this is what this slide is talking about here is what I was explaining before, is that when we look at that smooth average spectrum, it should fall within some specified tolerance of the target spectrum. Of course, we know it's not going to fall right on the target across all the periods, but we like it to get as close as possible. So, but here's the deal. I mean, you can see that right around our target period, our average spectrum from all the different individual response spectra is pretty close to the target spectrum. But if we move further, reduce the period, you can see that all of a sudden now we have some pretty big deviations here. And so it makes sense to think that we're not going to get our target across all periods. That would be pretty impossible and unrealistic to expect. So the idea is to try to focus on a period range of interest. So in other words, maybe I'd say if this is my target period, then maybe I could draw a line here and here and say within this window, my average response spectrum from all the individual response spectra is going to be within some specified tolerance of my target. So a typical window that is used by a lot of engineers is this range of 0.2 times the natural period up to 1.5 times the natural period. And the idea with this window is we're trying to account for the possibility that we can't really accurately predict what the true natural period of our structure is going to be before we actually build it. So let's go ahead and review some of the advantages and disadvantages of time history scaling. One of the advantages is it uses real earthquake time histories, and I have real in parentheses because these are the raw, true, recorded time histories from actual earthquakes. And that gives a lot of comfort to engineers to know that, hey, if I were to try to just make up a time history, which some people can do, um, I may miss some aspects of the seismic waves that we don't understand yet or don't know. But if we're using real earthquake time histories, then all of those fundamentals, all of those physics are inherently built into those time histories. Along with that, these scale time histories tend to retain their natural variances, which is in many ways a really good thing because we know that earthquakes have a lot of variability, and our ability to predict them with confidence is, well, it's stinky at best. And so when we have a wide range of spectral accelerations in our response spectra, that may be more representative of our true uncertainty with the problem. So a lot of people like this wider variance and the natural variance that's built into these scale time histories. And it can allow us to focus on one specific target period of interest, or even a window if we're interested in that. And of course, one of the most important things with this approach is that it's relatively easy to do, especially if you have the proper tools. Now, it used to be hard, don't get me wrong. Applying just a fudge factor uniformly across the time history in and of itself isn't bad, but picking initial time histories to fudge in the first place was really, really hard and time consuming. But now we have some new tools to help us, like the NGA West 2 online database that's housed at the University of California at Berkeley. It's got some really cool search tools that we're going to demonstrate on Wednesday in our lecture. And so, with these new tools available to us now, time history scaling is really not that bad. There are some disadvantages, though, that we need to talk about. The first disadvantage is that scaling, because there's so much variation, it's going to require a whole lot more time history records than if we had time history records that were really tight and close to our target response spectrum. So, the more variation we have, the more time histories we need so that we can capture all the possible variation. And with that greater variance in the time histories, you can expect to get a greater variance in your computed response. And again, this goes back to this concern now, because what if some of your models show your structure performs inadequately? What are you going to point the finger to? Is it poor design, or did it happen to be something in the time history itself or the ground motion? Was the ground motion unreasonably large? Who knows? And so it can be really difficult to find, the culprit in these instances. And then finally, even though it's pretty easy to do, I didn't say it was quick. Doing time history scaling the right way, because we're using lots of time histories, it can take a lot of time to do. And so, like for the homework assignments we're going to be having, it's not going to be too bad. But if you're doing this and getting paid for it in industry, you're going to spend quite a bit of time getting your time histories ready. Let's talk about the second method. And before I get to the second method, I do want to point out that there are other methods besides time history scaling and spectral matching to develop time history records for dynamic modeling. For instance, some experts and researchers use what are called Green's functions to develop completely synthetic time motions. When we go and visit engineers who helped design the seismic retrofit for the Utah State Capitol, you'll hear them say that the time histories they used in their models were all completely synthetic. I'm not a fan of synthetic time histories for some of the reasons we've already discussed. Personally, I think that there are a whole lot of things about earthquake ground motions that we really don't understand very well. And even though the process is pretty challenging, I mean, at the end of the day, we're still basically taking a wave and just adding some wiggles to it and calling it an earthquake. I'm a lot more comfortable when we use actual earthquake recordings and ground motions because I feel like at least that's grounded in reality and in nature. But with that being said, there are a lot of benefits to synthetic stuff, and we purportedly can synthesize and simulate motions from scenarios that we may not have a lot of data from. But then I would counter, if we don't have a lot of data from it, how do we know that the synthesis is realistic or representative of what really would happen? So anyway, and there's some other methods that deal with what we call physics-based prediction of time histories, where they try to simulate the development of time histories and the spread of seismic waves all the way from the rupture of the rock and then as the waves attenuate to your side. I mean, they're really sophisticated and advanced models and, pretty amazing and cool, but they're still definitely in development and definitely a research thing right now. So I don't see those being used in practice or design anytime soon. Okay, so that was my little detour. Let's get back to spectral matching. So spectral matching is where we're going to take a real or an initial time history that's in the time domain, and we're going to modify its accelerations. We're going to modify the acceleration time history using things that are called wavelets. So in other words, if that's time and this is acceleration, and we have some earthquake time history, however that looks. The idea is that we're going to come in and we're going to maybe take that and it's going to plot some response spectrum according to that actual time history. And we may come in and say, oh man, I have some target that looks like this. It'd be really nice if this point was up closer to my target. Okay, well, here's the deal. This is period, that looks like a tau, sorry. This is period T, this is spectral acceleration. Okay, so we know the period associated with that point there, and we know we need to get that up. So the idea is, what if we took another wave, and we use what are called wavelets. So these are just little guys that look like this. And they're, it almost looks like an echogram or something that you'd get from your heart. The point is that the spacing of these wavelets relates, it's a function of the period in the response spectrum. And the amplitude is a function of the spectral acceleration in the response spectrum. So the point is that we can add or subtract these wavelets to the actual acceleration time history to try to get this point up closer to our target, at least within a specified tolerance. But we've got to do it in a way that is mathematically feasible and doesn't create a scary Frankenstein time history. This idea of using wavelets to modify the acceleration time history was originally proposed by a couple of gentlemen named Lilhanand and Tseng in 1987 and 1988. But it really wasn't until the famous seismologist Dr. Norm Abramson developed a code called RSP match. in 1993 and made that available to the engineering and seismological community, that this method really started catching fire. And a lot of people started using it. And RSP Match was a useful program, but you see, Dr. Abramson is another one of these guys like Dr. Jack Baker. I mean, he's just a genius. He probably graduated from college when he was 10 years old or something. And you know, the fact of the matter is that RSP Match was really clear to nobody but him. And he didn't make any bones about that. He was straightforward and said, look, I'm happy to share this code with you, but I don't really have time to write documentation for this or to debug or troubleshoot your problems with the software that I create. And so there were a lot of spin-offs of RSP Match and different versions that were developed by different individuals. The most recent update that I'm aware of was done by Hancock and others in the year 2006, so it's been about 10 years. But they developed a method or a modification of RSP Match that's a little more stable and a little faster, I think. So the advantage of spectral matching is that we can take response spectra that look like the one we drew here, and instead we can end up with something that looks like this, that follows our target really, really closely. And so what's the advantage of that? Well, remember, the whole point of doing our numerical modeling of our structure or our soil is to try to hit it with a time history that is representative of the design ground motions that code says it should be capable of resisting. And then we want to look at the system for flaws or defects. When we do time history scaling, the variability in the time histories we introduce can be so large that looking for the source or the cause of defects can be really difficult sometimes. But when we have time histories that are really close to our target, now all of a sudden, if we see a flaw or a defect appear in our system, we can know immediately, okay, this may not necessarily be due to the time history. I think there is a flaw or a defect in our structural system. So the whole idea and the main advantage of spectral matching is that we're trying to reduce, that was crazy. We're trying to reduce the variability in the response. And why would using spectrally matching time histories reduce the variability in the response? Well, because, I mean, look, I have 3 time histories plotted with my target. And look how close the 3 time histories are to my target. If I plot the upper and the lower bound from all 3 of these response spectra, I mean, they're almost like practically right on top of my target spectrum. So that basically means that when I run my simulations in my model, theoretically, if I think of my model as a single degree of freedom oscillator, it's still getting hit by the same peak acceleration in every single one or across all periods of the spectrum. Now, the individual motions are going to be different, true, but the peak motions are going to be very similar between all 3 records. And that's really what we're after. So let's review the advantages and the disadvantages to spectral matching. In terms of advantages, we have less variability. Now, some people would call this a disadvantage, but again, if the goal of your modeling is to zero in on potential flaws of your structure and how those flaws could relate to the design spectral acceleration that the code is telling you to design to, then less variability could be a good thing. Because there's less variability in the response spectra, it usually requires few ground motions. Now, with time history scaling, where code may require, at least 7 time histories to use, the code used to require as few as 3 time histories for spectrally matched ground motions. I'm not sure if that law still stands. They may have just uniformly said you need at least 7 motions, regardless of which approach you use today. And like we said earlier, sometimes it's easier to spot design flaws in our structure or in our system when we have less variance in the input ground motions. Disadvantages: when we start adding wavelets or subtracting wavelets from or to the acceleration time history, we can get some pretty unrealistic and some wonky time histories. I like to call these motions Frankenstein motions because while we didn't just synthetically create the motion from scratch, we took a real motion and we may have altered it beyond recognition to the point where it's not a motion that we suspect any real earthquake would actually produce. Especially, by the way, if we're matching this to the uniform hazard response spectrum for the reasons that we discussed in the conditional mean spectrum lecture. If I force an earthquake time history to give me the response spectrum or to match a uniform hazard response spectrum, boy, that's a tall order for nature to produce that. Now, another disadvantage is that if we're starting to modify the actual time history of the earthquake, some of the valuable aspects that may have been inherently preserved in the time history might get removed. And a great example of that would be, for instance, let's draw a time history of, say, velocity. And let's say that I have a big pulse record of the beginning of my velocity time history, a directivity pulse. And boy, I think that might be important. If I suspect that my structure could be exposed to a forward directivity pulse, then I might want to have such pulses in the time histories I use in my modeling. But after, one of the things that I commonly see is after spectral matching sometimes, by the time we're done, that velocity pulse might look something like this. It gets filtered out or damped or whatever. It gets modified to the point that we essentially removed that pulse from our record. If you chose that record because you like the pulse that is in it, then you want to keep your pulse. So we want to be careful with our spectral matching to try to retain the aspects of the time history that are valuable to us. And, again, similar to time history scaling, spectral matching can take a lot of time to do correctly. You're going to see that it doesn't take a whole lot of time to run the spectral matching algorithm, but when you start asking the question, is this a feasible or is this a usable earthquake time history, you might find yourself starting to throw out a lot of the time histories that you're developing. And that's really what can take a lot of time, is running, rerunning again until you get a time history that you feel like you can use and rely upon. And finally, of course, spectral matching, because it is pretty much a black box, very few people, and including myself, don't understand very well the ins and outs of what's going on in the spectral matching algorithm. And as such, whenever you use a black box, no matter what it is, it's pretty easy to screw up and do something wrong if you don't know what you're doing. And I've seen this time and time again with being a third-party reviewer for time histories that have been developed for different applications. And yeah, it's rough. So part of the challenge in developing good times histories is selecting appropriate time histories to use and knowing when to throw out a bad or a wonky time history. So some of the factors that we should consider when we select time histories to use in our initial modeling. For instance, so by the way, I'm talking about now selecting time histories to use in either my scaling or my spectral matching. So we're saying, okay, we need initial time histories to use. Which ones are we going to pick? That's what I'm talking about here. So here's some things that we should consider when we select time histories. One, of course, we would want the recorded earthquakes to come from magnitudes similar to the earthquake magnitude associated with our design earthquake. Typically within plus or minus 1 on the moment magnitude scale. It would be nice if they were closer than that, but we'll take what we can get. Distance, of course, is important. We typically want the source to site distance to be within, plus or minus 10 kilometers of what our site is from the anticipated earthquake source. We'd sure like the faulting mechanism to be similar, but this is where you start to get to the point where, say I'm in Utah and the Wasatch Fault's a normal fault, so I go to the peer database or the NGA database and I say, I want time history records from normal faults. And you turn on that filtering criteria, and guess what? You're not going to get a whole lot of time histories because we don't have a whole lot of recorded normal faulting events. And so, in some cases, this isn't going to be as important. If I'm dealing with reverse or thrust faults, I think it's a little more important, and certainly subduction zone faults, though the NGA database does not have any subduction zone time histories in it. If I was designing for a subduction zone event, I would want to select time histories from a subduction zone source because subduction zones have much longer durations than crustal faulting events. We would like the spectral acceleration at our target natural period to be, within about 20 to 30%. And so, this is tricky too. This one, though, is not quite as important. You think it'd be really important, but when we do spectral matching, as you'll see, it could be further away. But typically, the closer the earthquake response spectrum is to our target initially, the better the match. This one's pretty important. We want to make sure that our ground motion was recorded on the same type of soil or the same type of rock, and that's usually based on site class. So remember, this was site class A, B, C, D, or E. We can filter the recorded ground motions based on their site class, and that way we could specify to get ground motions of just the same site class that our site is. And finally, we could specify whether or not we want to look for directivity effects. In the NGA database, these are referred to as pulse motions, not pool motions. Goodness. Pulse motions. So whether or not your time history has a pulse in it. So as I've mentioned a few times before, I really like to use time histories from the peer NGA database because they've undergone a lot of review and a lot of people have looked at them and vetted them, and the search functions that they provide are very handy. So, this used to be their database. I'm not sure if it's still active. The new NGA West database is this one that I'm circling right here. We've already introduced it or talked about it, but that's the database you go to search for earthquake time histories from the NGA West 2 crustal source database. To access this database, you do have to create an account and you will have a sign-in. It's free, there's no charge. They just want to track who's using their database. So this is interesting. How can you tell if your time history is good or not? We talked about picking and choosing time histories to use as the seed time histories or the initial time histories at the beginning of your analysis. Now that you're done with the analysis, you've created some of these time histories that are maybe close or match your target response spectrum. How do you know whether or not that time history that you created is a good time history? How do you know whether or not it's a keeper? So I was at a conference in Sacramento, California in the year 2008, and Norm Abramson was doing a question and answer session. And somebody asked him a very interesting question. They asked, when you do spectral matching, Dr. Abramson, how many of the time histories that you develop do you end up throwing out? And, this is the creator of the software. This is the guy who probably knows more about spectral matching than anybody alive today. And his response was, I throw out about 80% of my spectrally matched time histories. And you could hear the whole audience just go, ugh. Because if the master is throwing out 80% and only keeping 20% of the time histories he develops, man, most of the people in that room, I guarantee, weren't throwing out 80% of their time histories. I think his point was maybe you should put more thought into what you're calling a good time history and make sure that you're not giving your clients garbage. So it's really important then when we ask, well, why is this? It's really important that the time histories we develop are as representative of real earthquakes as possible. The moment we start to deviate from what we know is real is when we're starting to extrapolate and just flat out guess. And so we want to keep that to a minimum as possible. So here are a couple of things that I was taught to look for when evaluating your time history results. Again, you're not going to find any of this stuff written down in a journal article. You're not going to find it written down in a manual. These are the kinds of things that you just learn under the training and the tutoring of someone who's just a lot smarter than you or has a lot more experience than you. And that was certainly the case for me when I worked at Kleinfelder. One of the first things that they taught me was they taught me to plot the acceleration, the velocity, and the displacement time histories basically right on top of one another. So you have your three plots, 1, 2, 3. One is acceleration, one is velocity, one is displacement, and all have the same time scale. And the idea here is then, oh, this is going to get ugly. The idea is that you want to compare how the velocity and the displacement time history compare with one another. But then what you want to do is you want to plot, the spectrally matched time history on top of the same plot. Something that maybe looks like this. So you don't want to, you want to plot the pre-matching and then the post-matching time histories on the same plot. And that way you can see very, very clearly where there's going to be deviations, for example, in how the spectral matching cause your time histories to change. Okay. What we're really looking for is we want to make sure that significant peaks in our time histories aren't drastically shifted or altered in a way that we've really fundamentally changed the ground motion. Number two, we want to make sure that all the desired aspects of the ground motion, such as the directivity, are still there after the spectral matching. So if I go back, for instance, if my initial velocity record had a big pulse in it like that, I want to make sure that my spectrally matched time history also has somewhat of a pulse there as well. I want to maintain and keep that ground motion pulse in the record. Finally, we want to compare the pre and the post matching Arius intensity plots. These are the percent Arius intensity. I know, like in seismosignal, when you look at your ground motion parameters, it gives you an option. You have actual Arius intensity, which actually has units associated with it, or it has percent Arius intensity. And what you want to plot is the percent Arius intensity. This is going to be really similar to what we already did with these. In fact, a lot of people like to just line it up as a fourth plot. So we plot time as the same scale, but on this one, this is percent Arius intensity. Arius intensity usually is like represented with this capital I sub A. And the idea here is that, again, we're looking at post and pre-spectral matching and post. And Arius intensity, when you plot it in terms of percent, is going to vary between 0 and 100%. So all it is an indicator of the energy buildup in your earthquake, and it eventually will top out at 100%. What we want to see when we look at the post-spectral matching, you might see a little bit of difference, something like that. We want to see that the Arius intensity didn't deviate too much, because really what Arius intensity is indicative of is the energy run-up in our ground motion. It tells us where the earthquake is accruing energy. Some of you may be wondering what the world I'm talking about when I say Arius intensity. Go back to the ground motion parameter lecture, and I talk about what Arius intensity is. I mean, really, Arius intensity, all we're doing is we are measuring the area beneath each one of these cycle loops, and we're essentially summing up that area. So the more loops there are on each side of the x-axis, the more energy is being emitted by the time history. So this run up here is just like the integral or the accumulation of that energy. That's what Arius intensity is. So those are some of the things we look for. So some actual examples, for instance. Here's some plots I created. So these plots just show a couple of velocity plots. So you can see the dark black line, that was my spectrally matched time history, and then the little light dashed line, that was the pre-spectral matching velocity time history. So you can see, in this instance I have some deviation. Let's change my pen color. You see I have some deviation here, I have some deviation there, I have a lot of deviation here and here. When you start to see big deviations like that, that's not a good thing. Also, in my initial record, I had a peak down here, and that lined up well with that peak, so that's good. But then I had a big peak up here, but my spectrally matched time history doesn't peak till it's over here. So I actually had a time shift in my peaks, and so one could argue that we fundamentally changed the time history again. So this is why, I call this stuff bad. That would be an indication that, yeah, I would probably throw this time history out and try again. Now here's an example down here of a good match. So you can see that the peaks, they line up pretty well across the matched and the pre-matched velocity time records. There's distance, yeah. There's always going to be some distance between them. The point is, you want to use your judgment and say, that's not too bad. Certainly, you could see how that deviation and that distance isn't near as bad as that deviation from the plots above. So, if it were me, I would say, yeah, that's a pretty good match. I think I could keep that time history. So here's a couple of tips. In the coming week here on your homework, you're going to be running a software called SeismoMatch. On Wednesday, I plan to do a demonstration with SeismoMatch, and it would be really helpful if you guys had your computers with you and were ready to go to help, to follow along in that demonstration. A couple of things that are going to help you. In SeismoMatch, you can specify the tolerance. The tolerance is how much deviation from your target spectrum you can allow. If you're developing a lot of time history, say 7 sets of time histories, then you can have a pretty loose tolerance, 20 to 30%, and you're going to be fine. But if you have a smaller number of time histories you're developing, then you might want that tolerance to get tighter, maybe something around 10 to 15%. I want to tell you though that the tighter your tolerance is, the longer it's going to take for you to run your analyses. Not much longer, it'll just be a few minutes. But the less likely you're going to get a convergence on your spectral matching. And that leads me to my second tip. A lot of people make the mistake where they try to match the time history to the entire response spectrum in one run. And that's a really tall order for the algorithm to do. I usually prefer breaking up your analysis into 2 different passes. So in the first pass, specifying that you're going to match just between the periods of 0.01 second and 1 second. And everything greater than 1 second, you're not worried about. You're telling the program, don't worry about that, don't match that. So you're going to run that analysis and you're going to get your spectrally matched time history. That's going to be pass number 1. Then you're going to take that first match time history and use it as the input for your second pass, where now this time you're going to specify, your larger periods. Now, it doesn't need to be 10 seconds. You can match it out to 4 seconds or whatever your response spectrum is you're interested in. But the point is that in the second pass, you are going to increase your period window or your period range for your matching. So this range from 0.01 to 1 second is really going to get matched twice. And the reason is, if you look at any response spectrum, 0.01 second is really close to 0, and 1 second is out here. Generally, this is the portion of the response spectrum where you see the curve and it's coming around the top. Everything greater than 1 second is usually pretty logarithmic and just kind of spreads out. So because we have this curvy section up here, that's why we're doing 2 passes on it, because it's kind of hard for our computer program to try to match the response spectrum to that curvy portion. So in order to do this, just be aware that you may need to get into your default settings within RSP Match to specify these periods. So a final word of warning, software like SeismoMatch, and there's other software programs out there that do spectral matching. They've been simplified to the point that almost anybody with a mouse and any basic understanding of what a time history even is can come in and do a spectral matching job. Um, but if they treat it like a black box and they don't really have an idea of what's going on or the dangers or limitations of spectral matching, then it's like having a gun. If you don't know what you're doing, it's really easy to hurt yourself or to hurt others. So, again, the things I'm teaching you in this class, they're going to be useful to you, and it's going to be really nice for you to have this understanding. But I strongly recommend that you don't go out and start applying this stuff in practice and trying to sell these services unless you get under the guidance of some mentor that has some reputation and experience, and they can give you some training and counsel on how to do all this stuff properly. So with that, that's the end of this lecture. It's been fun. Thanks for watching. And feel free to leave any comments down below, or go ahead and shoot me an email and I'll be happy to respond. Have a great day.